Yeah, please settle down. Welcome back for the second installment of Kulkarni. Yeah, see, this is a serious lecture. Please keep silence. Okay, if you're not interested in it.
Yeah, okay, now I shall try to explain you the stages in which the symmetry got formulated in mathematics. Now we all agree that an equilateral triangle has the largest symmetry among all planar triangles. A square has the largest symmetry among all planar quadrilaterals, and so on. The phrase "and so on" means that for every natural number n has to be at least 3, all of us will come up with the correct definition of a regular n-gon. With some recall of high school Euclidean geometry, you may come up with even a definition of what a regular n-gon means. You have an idea of what a regular n-gon means, but you will come up with a definition. So, what are the characteristics of a regular n-gon? So, first of all the sides should be equal. All these sides should be equal. I am drawing the figure for n equals 5. Then, in addition, all the sides are equal is not sufficient. It's sufficient for a triangle for some degenerate reason. But even for a quadrilateral, just sides are equal is not sufficient, because you have a degree of freedom here. So in addition to sides, you have the angles. So all these angles are equal. And also the figure should lie in a plane. A triangle fortunately lies just in a plane, always, in some plane. But a quadrilateral you can bend. So you have to also say that it lies in a plane. So a regular n-gon is a planar figure whose all sides, there are n-gon as n sides, all sides are of equal length and all angles are equal. This would be a definition of a regular n-gon. And because these are all lying in a plane, we consider these as, we call these as two-dimensional examples. A three-dimensional analog of these examples, are you familiar with any of you? What is the three-dimensional analog of a regular n-gon? Polytopes. So, symmetric polytopes. They are well-known objects in mathematics. The Platonic polyhedra. Have you heard of Platonic polyhedra? So, it's a theorem that there are only 5 Platonic polyhedra.
Because Platonic solids. Platonic
Yeah. So let me start the beginning one. This is called a tetrahedron. Tetra means what? Wonderful, you know it. So in Greek, tetra means 4. So there are these 4 faces. So each face is an equilateral triangle, and they bound some 3-dimensional disk or disk-like object. In disk we usually think of a round boundary, but this is a polyhedral boundary. So this is a tetrahedron. The next thing is hexahedron. What is hexahedron? So that's a better expression for that. Cube is a better expression for hexahedron. Yeah, you will all agree. So both mean the same thing. So the hexahedron has 6 faces, and all the solid angles are equal, etc., etc. So to come up with a definition of this, you will have to think. But you can accept that these are the these are the symmetric objects. Then there is a dodecahedron, or otherwise, let me just say that if you take a midpoint of all these faces and join 2 midpoints, if the faces have an edge in common, then you get an octahedron. So this is like a pyramid with a square base. You take another copy of the pyramid,
It's a topological sum?
Sorry?
Topological sum of 2 tetrahedra?
What do you mean by topological sum? It's a union. Union of 2 tetrahedra joined on the base. The intersection is the base, union is this. And there are 2 more objects. Dodecahedron. Dodeca is 12 pentagons. So out of 12 pentagons you can construct this object. And it's dual in this sense. You take the midpoint of the faces and join 2 midpoints if the faces have an edge in common. It's called an icosahedron. Icosahedron has 20 equilateral triangles as the faces. These are very beautiful pictures, and I'm sure you have seen them in many contexts. And these are the objects which first of all caught the attentions of mankind. So in particular of Greeks. So Euclid's book 13 describes this polyhedra. A serious mathematical observation is that these are the only 5 Platonic polyhedra that can be constructed in a 3-dimensional space. Looking at the development of mathematics of the last 2000 years, one sees that these Platonic polyhedra has inspired a very large chunk of mathematics. Very large chunk. Now we have freely talked about the lengths of line segments, angles between 2 intersecting line segments, etc. But Euclid himself quite evidently does not wish to talk about lengths and angles. For length and angles are real numbers. And there are many stories about Pythagoreans and later Greeks which tell us that the Greeks were very wary about the issue of what real numbers are. That is, they were worried about how to define real numbers. I think they were comfortable with dealing with them for sure, but they did not know how to define a real number. It took 2000 years before Dedekind wrote a decisive paper in 1881, which I mentioned before, later improved by Cantor, explaining this issue of what the real numbers are or what they should be. The paper is called What Are or What Should Be the Real Numbers. In the introduction of this semi-philosophical paper, he argues that the question is not what are the real numbers, but it is what should be the real numbers. That is, what kind of experiences do we want the real numbers to account for? The main experience he wishes to account for is the following. Now, given a paper and a pencil, even a child just goes on drawing some figure. So long as it does not lift the pencil on the paper, he will draw some figure. In mathematics, this figure is called, there is a name for it, continuum. Continuum. And when you are saying without lifting a pencil, so that means there is some gaplessness that you can all feel. There are no gaps in this. Now, serious mathematical question is define gaplessness. You want a definition of what gapless means. So, in this context, he made this famous statement that the real numbers are creations of the human mind. The set theory was not the usual expression when he wrote this paper, but it did not matter. After all, everybody thinks that he or she knows what sets are. For him, a real line is a set with an additional structure. So, real line is first of all a set, and additional structure is in what in mathematics we call order structure. So you can say, you can always compare two elements, and this comparison is in real numbers we can call this less than or equal to. We can symbolize this by this just less than or equal to, and given any two points in this set, we can say 2 points P and Q. There is only either P is less than or equal to Q, or Q is less than or equal to P, or else P is equal to Q. So these are the only three possibilities. So this is what we call a total order on a set. So it's a certain relation, reflexive, transitive, and anti-symmetric. These are the words that are used. So this is the order structure on this set, and Dedekind came up with the precise postulates of which ordered sets now qualify, would you consider as real numbers. So there he talks about this, he came up with this supremum infimum ideas. Dedekind actually confused numbers and this order structure. That was clarified later by Cantor. But now let's think more in terms of Cantor, that he came up with this existence of certain elements in this set. So the idea was that a subset of this set is bounded above. Bounded above means there exists at least one element in the ambient set which is greater than or equal to all the elements in your subset. And given such a subset, Dedekind describes the postulate of completeness. This word completeness is used in 2 or 3 senses in mathematics, so you should be aware of this. This is completeness in the sense of Dedekind, or order completeness. And the other use of the word is metric completeness, which is due to Cauchy, which is different. This is order completeness, and the postulate is, given a subset of this set which is bounded above, it has a supremum. That supremum may lie in a set, may lie in the subset, or may not. So these are all clearly set theoretic formulations. So he enunciated the precise postulates about existence of certain elements in this set. The main theorem was to prove the uniqueness of this set with the additional structure. He says that Cantor Dedekind proved that we call this real line, not real number so far.
Do they live on that line?
Yes, they live, they breathe, they see, everything they do. But that is not relevant for mathematics. So this set is unique. That was the major assertion. Now, in what sense it is unique, one has to clarify. After all, if I write this, so this is not the same as this. So unique up to certain equivalence. I shall not go into this. There's little philosophical points. But these are it's unique up to a certain natural equivalence. Now, I said clearly here that there is a difference between the real line and real numbers. The first is a spatial notion. Real line is a spatial notion. Even a child can draw. And the second is the number notion. Number comes after space. So, how they come together so precisely is one of the mysteries of mathematics. Dedekind had not differentiated between these two notions, real line and real numbers. In a later paper, Cantor clarified this issue. The uniqueness asserted above was the uniqueness of the real line. So, uniqueness of this ordered set with this completeness property. Now, this real line can be given additional structure. Namely, given 2 points here, I can define what is, given 2 points P and Q, I can define what is P plus Q. Now, this plus is not the numbers. He just defined that there comes another point. P plus Q is another point. And similarly, P times Q is another point. And with this definition of addition and multiplication, it satisfies properties that you know that are held in rational numbers. So these are also you see, it's the addition of points, multiplication of points. It's not numbers at all, but that can be defined on this set. And this was the real numbers of Dedekind. And he proved the uniqueness of this whole structure, including order, addition and multiplication. Later on, Cantor clarified the point that this uniqueness is basically with respect to order only, already. And this uniqueness is the essential part. And then also how to define addition and multiplication, that is also some deep thought. But with these thoughts, so Dedekind proved the uniqueness of the real number system, and Cantor proved the uniqueness of the real line. And how these two objects come together, that is one of the mysteries of mathematics. Now, the definition of addition and multiplication is by no means unique. There are many, many ways. But afterwards, the uniqueness of the real line, real number system is up to certain equivalence. That equivalence I am not clarifying here. Yeah, I think it is that there will be a bijection of these two sets, so that order, if P is less than or equal to Q, their images, image of P is less than or equal to image of Q, and then the addition goes to addition, multiplication goes to multiplication. So if that happens, we say these objects are equivalent. So up to that equivalence, he proves that this is unique. So on the same real line, you can define these two different notions of addition and multiplication. But then you can prove that there will be a correspondence, bijective correspondence, such that the order goes to order, addition goes to addition, multiplication goes to multiplication. In this sense, it is unique. So this is really, you can say, beginning of set theory in mathematics, where he uses these sets very, very non-trivially. Uses the ideas of bijection between two sets and so on. So let us denote the real numbers by R. And with R under our belt, we can now give a definition, first of all, of the Euclidean plane. I said before that Euclid did not have a definition of the Euclidean plane. Now, what is the Euclidean plane? This is what we now tell you and you learn in, I think in your courses also you have learned, that Euclidean plane is first of all a two-dimensional vector space over the real numbers. Real numbers form a field. It's a two-dimensional vector space over a field. But the Euclidean plane is not the structure of a vector space, but it's the structure of the affine space which underlines the vector space. And on that affine space, we have another structure, namely distance. And that distance is a particular type of distance. We call that it's a Pythagorean distance. And that Pythagorean distance, so that is what you learn in the Cartesian geometry, that if you represent these 2 points by pairs of real numbers, then the distance between these 2 points is the square root of the difference between x coordinate square plus difference between the y coordinate square. So this is what we say, this is the Euclidean plane. But for Euclid, did not know real number, did not wanted to say what real numbers are, so he wanted to get around this. And yeah, that was the whole issue. Okay, so Euclidean plane for us is the two-dimensional affine space over the real numbers, further equipped with the distance function arising from the Pythagorean positive definite inner product. This is the definition that we give today. Without having R, the real numbers, Euclid was not in a position to define the Euclidean plane. He certainly experienced it, as we all experience. Every child experiences the real line. But he did not have the language to express what he felt. He did not have that expression. He tried to circumvent it by introducing the notion of congruence. He does not define congruence. You use the word two line segments are congruent in the Euclidean plane, two triangles are congruent, but you never define that congruence. So it's an undefined notion of congruence, and that congruence, this is the germ of this symmetry. So even for defining Euclidean plane, you need symmetry. And Euclidean plane is so attractive to us because it has a lot of symmetries. And allowing construction by ruler and compass. That is, if you take courses in algebra, you will come to know this ruler and compass. And Euclid's very first proposition is how to construct an equilateral triangle. So he says do this. So you have a ruler. So ruler, there are no markings. It's just a ruler. And the compass is given to you. So how do you construct the equilateral triangle? So you put one end of the compass here and the other end here, and so whatever that signifies, and then you make this as a center and draw this circle. Start drawing the circle, and then you put the one end of the compass on the other side, and then you draw this circle. Now if you take this point, then this is the equilateral triangle for him. So he constructs this equilateral triangle by ruler and compass. Now, I have not checked it myself, but I think he constructs n-gons up to 6. N is 3, 4, 5, 6. This fortunately suffices him for describing the Platonic polyhedra. He was very fortunate. Because for n equals 7, a theorem of Gauss will say a regular 7-gon you cannot construct by a ruler and compass. So he was saved somehow. As for the notion of congruence, it is now defined in terms of groups and their actions. This is the terminology that we have developed in mathematics, and this is a very profound formulation of symmetry in modern mathematics. The groups and their actions. Euclid's line segments have no length. Euclid's geometry is really a similarity geometry. In fact, some people after him, they try to define real numbers in terms of similarities. And so Euclid's geometry is not metric geometry. When we now teach or learn Euclidean geometry in the school and colleges, it's a metric geometry. The distance between 2 points is something that we assume we are talking about. But Euclid's geometry is not a metric geometry, it's only up to proportion. Euclid's angle is just what the word etymologically means. Angle means a corner. This is a Latin word. Corner is a special notion. So, two rays, intersecting rays, corner means this region in between. Corner means cone in our languages, in Sanskrit. So, trikona is a three-cornered figure. Chatushkon, Panchakon. Also, word for corner in Greek is gonon. So trigonometry. So that is coming from there. So angle for Euclid is really a spatial notion. It's not a number. And you see, now when we learn in high school, this angle is not, it's really not an angle, it's an angular measure. So what's the difference between angle and angular measure? Angular measure is always non-negative. Well, angle we are talking about minus 30 degrees, minus 40 degrees. So that is the difference. Now, Euclid's one of the great theorems is sum of the angles of a triangle is 180 degrees. This is not how Euclid would say that. he would say in terms of, first of all, at best, some of the angular measures is 180 degrees. And he did not know 180, he did not want to talk about numbers. So what he said was, they add up to a straight angle. So what is it? Yeah, I went a little faster. An angular measure between these two intersecting rays in a plane. There is not a unique region. This is one region and this is outside is another region. So smaller of the two is the angular measure. Smaller of the two. So this is the angle between these two rays and not this. Now for most angles, actually all angles which except the straight angles, this smaller region is uniquely defined. There is only one smaller region between two rays. Straight angle is for which there are two regions and you cannot define. This is the definition of a straight angle. Yeah. So straight angle is a line and a point on it. So a point defines two rays on the line, and this is the straight angle. And when Euclid proves some of the angles of a triangle theorem, he says something about parallel. This is the Euclid's proof. That you take this, now this is the same as this. Parallel lines. And this is the same as this. And this is the third thing. So what he's saying is that if you take these three corners and put them together, then you get a straight angle. Okay? You don't have to talk about numbers here. These are the actual spatial regions. So that, that is this original theorem. So Euclid talks about straight angles. Euclid also talks about right angles. Right angles doesn't mean 90 degrees. Now given an angle, you can extend one of the rays and make it a line. So given an angle, there is a complementary angle. And right angle is one for which the angle is congruent to its complement. Yeah. So that is sufficient for Euclid to develop lots and lots of his geometry. Straight angles, right angles, and ruler and compass. So with that he formulated this whole beautiful structure.
Congruence was not defined.
Congruence was not defined.
So he had motion in his mind, move it.
Yeah. No, so that is, he certainly had that in mind. So certainly he would say that this is the same, this is congruent to that.
He did not come across the congruence.
Yeah. Yeah?
He not defined congruency.
It does not define congruence. So there are these rules for congruence of triangles. SSS, side, 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 angle, side. These are the rules. Congruent is not defined. It does not actually define congruence of two subsets of the Euclidean plane. Now with our...
It came from those onwards?
No. So with our groups around, now we can say even two subsets are congruent. And this group under consideration is the isometries of the Euclidean plane. And two subsets are congruent if there is an element in the group which carries this into that. So you can define it even for subsets. Okay. Similarly, Euclid's circle. Circle is which you can draw with a ruler and compass. So, taking this, and this is whatever this region, this compass, you put this center and you can draw this circle. So this is one of the postulates of Euclid, that through a given center, and he would call this radius, but radius is not a number. Given a point and a radius, you can draw a unique circle. That is his postulate. Unique circle. That is his postulate. So there is one more issue. It concerns an orientation of the Euclidean plane. Euclid may have felt it, but probably decided against mentioning it at all. Again, because he did not have the necessary language to express it. Euclid's triangles and circles carry no orientation. So this triangle, this is the figure, but this orientation is giving these directions to the lines and calling there are two orientations, and this is a spatial notion, but we transform that into a number notion, positive and negative. And we have to make a choice. So what is this? When is it positively oriented?
Anti-clockwise.
What is anti-clockwise? So when the bounded region, so triangle has two complements, a bounded region and unbounded region. So in the bounded region, if an ant starts crawling on the boundary, it will feel that bounded region to the left. And that is how we teach also. Orientation for Green's theorem, Stokes' theorem. Orientation is an extremely important issue. Without that, understanding of Green's theorem is not complete. And how is that Green's theorem? How do we say that when we teach Green's theorem? If an ant starts crawling on the boundary, whatever that bounded region lies to the left. That is sufficient expression. So, said theoretically, it's not a definition. But again, I would say that you do not have to use set theory all the time. To express it, to communicate it, you may very well use different expressions. And this is also true for writing papers. Papers, if it has to be published in a journal, you have to use set theory. You have to give the definition, and then prove it. But that one paper is not understandable to a mathematician working in some other area. A PDE person does not know what topology means. A topology person, it doesn't deal with any numbers at all, so it doesn't know PDE. So the languages are different, and to make connections between these languages is very, very important issue for those people who are thinking about these issues. So this again illustrates that the set theory is only an expression for mathematics. The alternate expressions may be freely used for better communication and enjoyment of mathematics. So far we did not say anything about Euclid's notion of congruence. Actually, we have implicitly used symmetry in various layers in the above discussion. The set theory allowed us to formulate symmetry itself in terms of what we now call groups and actions. And this is a profound development in modern mathematics, and to which we now turn. And with this definition, we can even give the definition of what an Euclidean plane means, and so on. So groups and their actions. How many people have not studied groups in their curriculum so far? Yeah. Okay, so this is an next notion that you will study probably if you continue with studying mathematics. Probably it should be introduced even earlier, I do not know. And it could be even explained in high school in whatever crude way you can explain that. It is really explaining symmetry. So, in now set theory, given a set X, fixed set X, then in set theory we have sets, an element of a set, and mapping between sets and functions. So given a set X, it gives rise to several other sets by using actions of set theory. So one is end X. So these are all functions from X to X. So function is a technical word. Given a point in a domain, there is one and only one point in the range. 2 points in the domain can go to the same point. Not every point in the range may be an image of a point in a domain. So that is what function means. And f is a function. So this is another set. From this set X, we came up with another set. Actions of set theory tell you that this is also a set. We shall allow this in our discourse. End X. And ought X is a subset of this, and it's a function, but a special type of function. It's a bijective function. So all of you, of course, know bijective. I need not define it here. And now you see these are functions from the set to itself. Domain and the range are the same. So this function defines other functions. So from X to X, you go by F, but again I see the same X. So I can iterate this. Now F composed with F, this we shall denote it by F square. This is like a multiplication, but this is not multiplication by numbers, this is just a notation. And F square may be a very completely different function. Yeah. So if you take the function, what you study in calculus, x goes to x square. What is F square? X square square. Yeah, a better example is x cube. X cube followed by x cube. It's not x cube multiplied by x cube. X cube multiplied by x cube is just x to the 6. But x cube followed by x cube is x to the 9. For that x square example, the two answers happen to be same. Yeah. So this f square is another object altogether. You can iterate this. So this is the iteration. So f square, f cube, etc. And then now if it is bijective function, you can also consider the inverse function. bijective by definition means the inverse exists. And it is unique. And that's also a function from x to x. So you can also take that f inverse and again iterate that. So you can, so to speak, get a copy of the integers in this set of functions, or some map of the integers in this set of functions. So this integers is this set, and these are the functions. So this is a subset. So you get a map from here to here. That number integer n goes to f to the n. And this map preserves the structures here. You add these two numbers here. So n plus m will go to f of n followed by f to the f to the m, and that is the same as f to the n plus m. And so this is in case the f is bijective. Otherwise the whole numbers, otherwise you can talk only about the function and its iterate. You cannot take the inverse. So given a set X, we can define these two other sets, and this set is now a group, is an example of a group. So given any set X, we come up with a group, the set of all automorphisms. Aut stands for automorphisms. Now X is a finite set. Suppose X is a finite set containing n elements. So that automorphism, we have a different name in mathematics for that. It's the permutation. So permutation is a special case. That word is used when the set is finite. If the set is infinite, then again we can use that word. It's different expression after all. So that is that. And so on and so forth. So this is how we come up with groups. And if it is just if it is not invertible, then this end X is called a semigroup. That also develops in computer science in many ways. It's called a monoid. In mathematics, I think monoids were not used very much, as much as the groups were used. But with computer science, with the enormous development has taken place. So mathematics now consists of sets, structures on sets, and mappings between structures equipped with sets equipped with structures. This is how we have formulated the whole mathematics. Sets, structures on sets, and mapping between sets with structures. Yeah. So let me take a concrete example. Take the Euclidean space. Denoted by E, this script E, E2. So this is the Euclidean space. Now, the structure on this, there are various structures. So just by ruler and compass defines a similarity structure. With the distance around, we get metric structure. So take the metric structure, for instance, and so if X is any set with any structure, then we can consider set of those functions which preserve the structure. So that is some subgroup of Autex. And so let's take the distance of the structure on Euclidean plane. And now sigma is the distance. So sigma is the distance. So let's call that d. D is the distance. So what is that distance? You have to express that set theoretically. So given 2 points, you can come up with a formula for a distance. But what is that distance itself? It's a mathematical entity. It itself is not a number. It's not just a number. Given 2 points, it produces a number. It itself is not a number. So what is this distance? Any people who have learned this? So it's some function. So it's a function. What is the domain of this function? Pairs of points in the Euclidean plane. So this is a function from E2 cross E2. And what is its image? Non-negative real numbers. And it satisfies some additional properties, and so on. And now, first our major theorems in beginning mathematics is people did not talk about this. So a function which preserves this distance, in physics we call that a motion. In mathematics it's an isometry. So these are again two different words explaining the same idea. So the isometries, so similarly we can define n-dimensional space. So the isometries of e to the n. So first of all, we actually get epsilon 1 also. You try to analyze what is epsilon 1. What's the Euclidean line? So you try to analyze that, and then epsilon 2 is that this is a degenerate case that we don't even notice, but it's important to notice it when you develop a theory. This is what we notice, and this regular n-gon, this has lots of symmetries. What does it mean? The isometries which carries this into itself. That is, there are many of them, and in this case there are these n rotations and n reflections. So this is the dihedral group. Such that f carries this given rectangle or given n-gon, and f an isometry. So everything expressed in terms of set theory. So this D2n is one of the groups that came to our attention, and these were discovered by painters. So the classification of finite subgroups of Euclidean isometries is essentially D2n and its subgroups, which is a subgroup of rotations. So it is called Leonardo's theorem. I think this Leonardo is the same as Leonardo da Vinci, or you may know it better. Yeah, Leonardo da Vinci was a great painter, a Renaissance painter, I think in 16th century. So this he actually made such sketches, and actually there is enough thing to say that he really knew D2N. And so now, which will come now as a theorem in mathematics, that the finite subgroups of Euclidean group of motions suppose G is a finite subgroup so classification imply G is blah blah blah. So it's essentially D2N or Cn is the cyclic group and n going from 1 to infinity. For 2 there is no geometric object, there is no 2 gone. But in group theory there is. so in a way group theory completes this geometry. Okay, so these are the kind of theorems that were discovered long before Galois. Galois did not start group theory. He noticed the symmetry and he really came up with symmetry of a different object, of roots of polynomials. And he came up with a serious theory that I shall probably will not have time to describe that. So, the classification of finite subgroups of the group of motions of the Euclidean plane was known in the Middle Ages. They are essentially this full group D2N of symmetries of regular n-gons and the cyclic subgroup Cn consisting of only of rotations. This is attributed to Leonardo in the 15th century and known as Leonardo's theorem in geometry. Based on this classification, the infinite discrete subgroups of epsilon 2, this is another thing. There will be infinite groups now, but we ask them to be discrete. And among these discrete groups, there are these well-known 17 wallpaper groups. And these groups are actually seen, people say, in Alhambra's paintings. Alhambra is a town near Granada, to the south of Spain. And there are this is the high point of the Islamic art in the 15th century. So these paintings are considered a high point of the Islamic art. And if you see the underlying groups which are exhibited there, they claim that they exhibited all these 17 wallpaper groups, which is the actually classification theorem in mathematics. So finite subgroups as well as discrete subgroups of this group of Euclidean motions are actually classified. And they are long before even group theory was mentioned. The classification of finite subgroups of Euclidean three-dimensional space was also essentially known, and they are essentially connected with the Platonic polyhedra. They are essentially the symmetry groups of Platonic polyhedra, and based on this classification, again the infinite discrete subgroups of epsilon 3 can also be classified. And these are seen in Brave's classification of symmetries of crystals. So this is a subject matter in chemistry, and Brave was a contemporary of Galois. So he discovered these symmetry groups in crystals. So you can see a lot of contribution to mathematics has come from people who were not professional mathematicians. This also shows one of the directions in mathematical activity that start with interesting mathematical objects. And what does interesting means? One possible definition, which has a lot of symmetries, whatever that means. And understand those symmetries. What does understanding symmetry means? Classify automorphism groups. And this is the mathematical activity. A significant development in understanding symmetry, which occurred in mathematics in the late 19th century, is the definition of abstract group. So, in actual experience, we start with an object, we find it interesting, we consider it symmetry. So, we starting from object, we are going to its symmetry group. But now, further abstraction, you just consider the abstract definition of what a group should be. And at least these two definitions you should get from this talk: a group and their actions. So these are genuinely mathematical definitions. They are taught usually in courses in algebra, but they go far beyond algebra. They really bring together the whole category of mathematical thought. They bring the very idea of symmetry. It's a formulation of the idea of symmetry. So here on page 11 I have given you a definition. It's just a set. A group is a set with a binary operation. Means a map from G cross G to G. And for simplicity, the pair goes to this image. We call this image as A times B. It's like a multiplication. We just call it. And then this map should have the property that A times B times C is A times B times C. And there should exist an identity, existence. A dot E equals E dot A equals A. And an existence of inverse. For every A, there should exist an inverse. So what I call art X is a group with respect to this definition. And now the game changed in 20th century. You start with groups and you classify their actions. So, why was this concept introduced in the action and the abstract group? So, I have given some reasoning here that a group may start acts on X, then some subset may be invariant. Group restricted to that subset, that mapping may not be injective, so it may not be a transformation group. So this notion of action was useful in classifying this, was in considering this. And the same group can act on different sets in first of all. So these are different sets on which the group is acting. More interestingly, same group can act on the same space in two different ways. So what matters is the actions and not these two separate objects, groups and the space. So because of this, these groups and actions were introduced, and so on and so forth. And so conscious thinking about groups and their actions has led to the unification of large chunks of already accumulated mathematics and led to new directions of research. So so-called all representation theory is a late 19th, 20th century product. Okay, so this is how groups came into mathematics, I will explain. Now a serious theory came in Galois' work, in which he described the basic difference between solvable groups and simple groups. He did not start with groups to start with. He was interested in solving polynomial equations. And it's a serious theorem that we study in Galois theory, that a polynomial of degree n with given coefficients, then the roots of this polynomial can be expressed in terms of taking nth roots of some algebraic finite expressions of the coefficients. That is with the solubility of radicals. That is possible if and only if he associated a corresponding group. If that group is solvable in the notion of groups. So you are using the word solvable in two different ways. So it's like the word yoga, you know. People say this is yoga, that is yoga, but these yogas mean different things in different places. So solvable group and solvability of equations by radicals are two completely different ideas. Same word is used. But the solvability of polynomial equations by radicals is now transformed into equivalent language of solvability of groups. So this is the basic difference in groups themselves, solvable, and then opposite of that, there are again technical things, but solvable groups and simple groups. And then simple, so conjugacy, normal subgroups, etc. Then the classification of simple groups, that was the high achievement of the 20th century mathematics. Late 19th century and whole 20th century. And they did not classify the whole simple groups, all simple groups, but what they call the simple Lie groups. That was the first achievement, and the finite simple groups is the other achievement which came much later. And in terms of that, we can really understand a great deal of mathematics, no matter of what branch you consider, whether you call it analysis, topology, geometry, or whatever. This symmetry group is a way of looking at the whole of mathematics. Okay, that's enough.